Hello once again. Today I'm recording from my son's room, and we'll work problem D3. It's another example using the heat equation. So if some of you guys recognize this screen, you need to put your controllers up so we can get down to business. Okay, let's go ahead and look at this problem here. This is D3. What we have given is a wall, one-dimensional. The length of the wall or the thickness is 0.3 meters, and at some time t, we know that the temperature distribution in the wall can be represented by this equation here, A plus Bx plus Cx squared, where A is 200 Celsius, B is a negative 200 Celsius per meter, C is given as 30 Celsius per meter squared. And all three of these, A, B, and C, are constants. The conductivity of the wall is known. It's 1 watt per meter Kelvin. In this problem here, the energy that's being generated is equal to 0. Okay? So then we're asked to find Q dot double prime at x equals 0. And here again, the double prime here means per area, per length squared. And then also in part A, find Q dot double prime at x equal L. And then find the energy that's being stored per area. Okay, then part B says, well, find the convection coefficient at L, at where x equals L, if you know that T infinity is equal to 100 Celsius. Okay? So we'll start by looking at our geometry. We'll just call it a schematic here. So what we have is Q dot double prime N at x equals 0. We have some energy being stored inside the wall. And then we have Q dot out at x equal L, which is 0.3 meters. I'll just call it L for now. And also on this side we have some convection. So I'll just say H and T infinity out here. Okay? So part A said, well, alright, what is Q dot double prime at x equals 0? So we know from Fourier's law, this will be solution. From Fourier's law, we know that Q dot double prime is equal to minus K times dt dx. Okay, and double prime is here because I divided through by the area. Okay, well, the temperature here again is given by this equation here, so we can take the derivative with respect to x of the temperature, and if you do, okay, let's look at it. Dt dx is equal to, okay, the A would just go away, we'd have B plus 2cx. Alright, so in part A, if we want the temperature, or the Q dot double prime at x equals 0, we would just substitute a 0 in for x. So then dt dx at x equals 0 would just be equal to B. So B is known, the conductivity is known, so we can substitute B for delta T delta X and substitute for the conductivity. If you crunch those numbers out, you would see Q dot double prime at x equals 0 is equal to 200 watts per meter squared. Okay, and then we can do the same thing at x equal L, where we just substitute a 0.3 meters for x, and if you do, here again, C is known and B is known, so it's just a matter of substituting that into your calculator and crunching out the number. So if you do that, what you would get is that Q dot double prime at x equal L is equal to 100 and 82 watts per meter squared. Okay, so now we have a Q dot double prime at x equals 0, Q dot double prime at x equal L. Okay, so let's see, also in part A they wanted the energy stored. So here, if we just go with an energy balance on our geometry here, what we would have is energy stored. We'll just call it the first law. Energy stored, let's say dot double prime, is equal to energy in dot double prime plus the energy generated dot double prime minus the energy out. Okay, and here again there is no energy generated, that was given. We've already shown what the energy in is. It's 200. The energy out is 182. So you substitute into this equation here and you would see that the energy being stored is 200 minus 182, and that's watts per meter squared, and you would get 18 watts per meter squared. Okay, so that is the energy being stored. Okay, so part B. For part B, what we have here, the question is, what was the question? Find H at L if T infinity was 100 Celsius. Okay, H is what we want. So let's look at the surface here. At x equal L, we have Q dot double prime out, and that's going to be equal to Q dot due to convection. Okay? Because we're going to have some air blowing over this, or some fluid. Okay, so what we know then is that Q dot double prime out is equal to Q dot double prime convection, which would be H times T at L minus T infinity. Okay, so H is what we're trying to find. We already know Q dot double prime out. We just calculated that from part A. That was 182. So the question here, and T infinity is given. So we can check that one off, we can check that one off. So the question is, how can we get TL? Okay, well if you look back at what was given, the temperature distribution is given. So if you want the temperature at L, that location, which is what we need, you just substitute 0.3 meters in for X. And you can actually calculate the temperature at L. Okay, so if you do that and do the math on it, TL comes out to be, well, I'll just go ahead and do it here real quick. A was 200 Celsius plus B, which is minus 200 Celsius per meter times X, which is 0.3, plus CX squared, and C was 30. Let me put it down here. 30 Celsius per meter squared times X squared, which here again is 0.3 meters squared. So you put that in your calculator, crunch the numbers out, and you'll see that T at L is 142.7 Celsius. Alright, so now we have TL, we have everything we need. We can substitute for TL right here. T infinity was given. Q dot out double prime we calculated from part A, so we can calculate H now, the convection coefficient. And that would be 4.3 watts per meter squared Kelvin. Okay? So that is part C. So let me show you one more thing here that's kind of interesting. If you wrote the simplified form of the heat equation for our geometry, which here again is just a rectangular wall. But if you wrote the simplified form of the heat equation for one dimension, you would have the change in temperature with respect to time is equal to K divided by rho C, the specific heat, times d squared T dx squared. Okay? So if you took the second derivative of the temperature with respect to x, what you would get is that is equal to 60, the value. And then of course you would have K divided by density times, or divided by the specific heat. Okay. Okay, what this would show you is that the temperature is actually increasing with time. Because if you plotted temperature versus time, you would either get a positive slope, or you could have a positive slope, a negative slope, or zero slope, meaning it wasn't changing. But if you have a positive slope, that's going to show that with time temperature is increasing. Negative slope would show that with time the temperature is decreasing. Okay, so this is problem D3. Okay, once again, I'm broadcasting or videoing from my son's room. I hope you guys enjoyed the problem today. I'll see you next time. Until then, be good.